Hello engineering students, Mr. O again, and today we're going to go into now a bit more discussion and more detailed stuff about method of joints. We've done quite a few of these already, all the way through simply supported beams, overhanging, axial loads, UDLs, as well as shear force diagrams. And we've done a couple of examples on method of joints, but focusing more, I'd say, I'm going to block this section out, focusing more on sort of the edge of a truss, looking at the external forces and how they influence the internal forces around a specific joint and how that transfers into the internal forces experienced in a specific member. Today, in this example, we're going to look at an example question that asks you to do that, where the question actually says determine the reaction through the members C and D for this really simple truss. This is effectively, now we kind of looking at just that top part. Imagine we just have that top part there. So we only have that section there in the top where, let's say, C is. And so the question is asking us to find the reaction through that member and that member based on this force that's been applied to the top of that joint there of these two members. Okay, with a theta angle of 50 degrees between those two. Now, based on what we see, the first thing I do when I start working on this type of question is list the members I'm going to be solving. So obviously I'm going to be solving for C and I'm going to be solving for D. And my second thing that I would do is I would redraw this. So just like that is drawn there, I'm going to draw this here and like that. Now, based on the way it's drawn, and we aren't told anything else, I would assume that that is equal. C to the vertical and D to the vertical is an equivalent degrees there. It's half of that 50. I'll draw that 135 not kilonewtons. I've written kilonewtons there. Let's not do that. Let's just make it newtons. It's going to be simpler and easier. So I've redrawn it. I've got a good idea of what I'm looking at. Now, it's going to be quite tricky doing it like this. So automatically what I see is two triangles. What I see is two triangles looking something like this. Now I'm going to draw that as if it's like that, and that as if it's like that. And I'm going to make the assumption, I'm going to call this, if I'm going to do a method of joints, I'm going to call this C and I'm going to call this D. And what I'm going to do is I'll maintain that as 135 newtons. That was 50. I'm going to call that 25 and I'm going to call that 25 degrees. Now this is a dotted line. This is not an actual line. I've just imagined that that is split into like that. Okay. So the first thing I would do is probably assume that I have a force holding up that. Obviously, if this is going to be a frame, if this is going to be a top of a triangle, it's going to have a force holding it up there. Let's say A and B. I'm just using this as an example. So let me do like a mini moment calculation to try and solve what the external force is applying, the reaction applied to C to hold this frame up. And I think the best way I'm going to do that is to assume the distance between C and D, I'm going to call that X. And this between C and the vertical of C, equivalent force vertical of C, I would say is half x, and I'd say the same on this side. The distance between this and the vertical of D would be also half x. So let's just assume that. I think that's going to be the quickest and easiest. So what I'm going to do now, straight up, is I'm going to imagine between C and D. Imagine C and D has a beam. It is a beam at the bottom. I have D there, I have C there, and right in the center, I have a force of 135 newtons, and the distance is half x to there, and the whole distance is going to be x. So the sum of the moments of that beam equal 0. My sum of the moments around my counterclockwise will equal the sum of my moments clockwise. Yep, does that make sense? And effectively, if I take moments about C, I want to try and find D. So if C becomes my pivot point, I'm going to work out, is that force causing my beam to go clockwise? If it's pivoting like that, and is the force that's holding up this in its vertical position causing the beam to pivot that way? So let's have a look. Counterclockwise moments. I would say pivoting around C, counterclockwise, because I've basically written it like that, counterclockwise equals that. If I want, I could also just do this, plus sum of the moments clockwise minus sum of the moments counterclockwise. Pivoting around C, sum of the moments around C, clockwise, going this way, will be force times distance. 135 times 0.5x. Yep. And this, I'm going to assume it's up, because we automatically assume, because we don't know what it is, that it's going upwards. It would be the force at D, and I'm going to say it's the D, the external force pushing upwards times x. Get my calculator. What's half of 135 times 0.5? 67.5 x minus the force pushing onto that joint there, the force of D, x. I don't actually know where to go from there, so I'm going to take my D to this side. Force D x equals 67.5 x. These two cancel out. My force D pushing upwards is 67.5 newtons. Pretty much, we could have seen that straight away. If that's going to be the exact same distance, it's going to be the same angle. 135 divided by 2 is going to be 67.5. To prove that I know then what the force at C would be, I do the sum of the forces vertical equals 0. Sum of the forces down equals sum of the forces up. I'm going to leave that like that, because all the force down is 135 equals the force of C plus 67.5. That goes over to that side. 135 minus 67.5 equals force C. The force at C is 67.5 newtons upwards as well. There we go. I now know the equivalent force, external force, just like my last question that I've done, and the same here, the question before this. $67.5, and that is D. This is C, 67.5. Okay. How to solve this next part now? Now I'm going to do a method of joints discussion. So I'm going to look at the method of joints, and I'm going to look at, where should I start? I started solving D, so let me go straight to D. And I will look at, I'd normally start where I can. I've got that as an idea there. I would normally start going the sum of the forces vertical. You can start sum of the forces horizontal, but we don't really need to, because what we're trying to do is you're trying to solve the force over there. And so what I do is I then look at the joint. I look at the joint and I see that externally I have a force of 67.5 newtons pushing upwards, which is into that joint D. But I'm actually trying to solve the force in this here. And what that is, I don't know what it is. Okay, so automatically in method of joints, what I do is I assume that that member D is in tension. If it's in tension, it's moving away from the joint. And the vertical equivalent of that, if this is 25, then this is going to be the opposite. This is going to be the adjacent. I want to solve that. But if I'm doing method of joints, I need to work out the forces that are completely and utterly vertical, in that this would be the adjacent over the hypotenuse. So this would be the hypotenuse, D would be the hypotenuse, and the vertical force would be the adjacent. Adjacent of hypotenuse is cos, so effectively this force adjacent over hyp equals cos 25. I know this is normally counterintuitive. Normally what we do is if it's vertical, we say it's sine, but that's if the angle is here. Now the angle is here. Technically, I could say cos 25 because this is the opposite, but if I had the angle there, which I can work out pretty easily, it's going to be 90 minus 25. I could call it cos 65. It's going to be the same, sorry, cos sine 65. So I could really do, if I put 90, because the sum of all the angles within a triangle is 180. If that is 90, and that's 25, that would be 65. So I could say it's sine 65, and this will be our opposite, but I'm going to stick to just using the cos. So this is going to be my force of D, but the vertical equivalent, which equals, that's my hyp. That's my hypotenuse of this. And adjacent over hyp equals cos. Therefore my adjacent, because I'm looking at the vertical, that is the vertical itself, it is the adjacent, which also equals the hypotenuse cos 25 in this particular sense. So the sum of the forces down equals sum of the forces upwards. If we have a look at this joint in D there that I have drawn here, I need to only work with the vertical forces. Therefore, I look at the resolved vertical force of D. The resolved vertical force of D is the adjacent of that angle. Therefore, it is actually the equivalent of hyp cos 25. And it serves me well because I'm trying to find out what the hypotenuse is to work that out. So if I look at that joint, I've got the external going upwards. I've got this going upwards. Therefore, I've got nothing going downwards. So my force up is going to be 67.5 plus my force vertical of D there, my resolved vertical force there, is actually the hypotenuse cos 25, because my angle is actually there this time. It would normally be sine because the angle is there, but now that the angle is there, I'm actually looking for the adjacent. 67.5 plus force D, or force D itself, that's the angle there, cos 25. Negative 67.5 equals force D, divide that by cos 25. The force, the reaction in this particular force, the force is cerebral nose negative, so it's going to be compression, and 67.5 divided by cos 25. 74.48 negative newtons. Being negative means compression. So technically, instead of going away, when it's compressed, the force into the joint at D would be pointing in that direction. So that is my force for the force within that member D. I'll quickly solve the other one. So if I go method of joints in C, is going to be pretty much the same approach. I look at the joint there, I've got that, but I can only work with purely vertical. The sum of my forces vertical equals 0. I forgot to put that there. This is 67.5 again. I know what C is. It's an axial load, but I can only work with the vertical equivalent. Its vertical equivalent, just like here as well, this is 25 degrees. This is going to be the opposite. This is going to be the adjacent. It's going to be another cos to work out that one there. And so this is going to be the adjacent, but the adjacent equals hyp cos 25. Let me do the same one. So force, the sum of the forces down equals the sum of the forces up, because this is an equilibrium. No forces downwards. Again, 67.5 plus force of C, which is the hypotenuse, cos 25. Again, negative 67.5 divided by cos 25 degrees equals the force in C. And that again also is there we go. Again, it is negative, therefore negative equals, it is in compression. When you're doing a truss type calculation, you always state what the force in that member, the force that that member is experiencing internally. I'm going to do something quickly though. I'm going to calculate this as if I used sine 65. Let's just verify that if it's going to give the same answer. You saw that this answer is 74.48 rounded up. If I change this to sine, sine 65, the exact same answer. Just to verify that. It's just showing that that's the opposite, and I'm looking for the adjacent. If I worked out 90, because it's 90 degrees, minus 25, it'll give me 65 degrees. 65, if this is the opposite, it'll just be sine. I think, there we go. That's the answer for this question. And I hope it made I hope it made sense to you.